Welcome everyone, this is Matteo Matteucci and today I will talk about federated learning. This is a tutorial within the AI-SPRINT project. Within the AI-SPRINT project we have studied a design framework and a runtime framework to develop AI application to the continuum between the IoT, AI-enabled edge sensors and the classical cloud with some layers in the middle, which is usually occupied by edge servers. The goal of the project is to allow an efficient development of machine learning systems. These systems are characterized by a lot of components where machine learning actually occupies a minor part. The most of the effort is usually developed in the configuration of the system, development and deployment of the system, and the servicing of the infrastructure. Within this framework of the AI-SPRINT project, today I will talk about privacy-preserving continuous training, which means to be able to train within a distributed framework, possibly between edge devices and cloud devices. Why we want to perform training and inference on edge devices or even on sensors? This is because data is born at the edge. So by processing directly the data at the edge, we reduce the latency of the result, we improve the efficiency of communication, we remove some loss in energy due to the multiple partners in a client-server systems, and we increase the privacy. In particular, the latter is relevant to be compliant to the GDPR and other privacy regulation laws. If we think at classical deployment of AI systems, usually we can distinguish between training and inference. At training time, usually this is performed on cloud or on-premises computers where data is collected, labeled, and models are developed. Next, the models are deployed on the field to perform inference. And here it comes the idea of performing AI at the edge, because by the use of specialized accelerators and embedded devices, it is possible to perform inference at the edge. Some examples are, for instance, smart cameras that can recognize that a person has entered an area, or on-device facial recognition systems or object recognition systems, where again in this case data does not leave the device. Onboard systems like those of autonomous cars, where data are processed and information is extracted to perform self-driving tasks. And finally, all sorts of applications that require to process images and data with low latency on drones, robots, or other systems. Then, in parallel, we have the cloud, where data is collected and models are trained. Now, if we look at this dichotomy between training and inference, we see that the computation is performed in a sort of partitioned way between cloud and edge devices. But this is not true anymore. We have a more complex scenario with end devices like smart sensors, smart devices, smart glasses. We have the edge with gateways, routers, base station, which is powerful enough to perform both inference and training. And then we have the cloud, where we have plenty of computational power. In the recent years, a new paradigm has evolved, with several layers going from the pure cloud intelligence to the all-on device. When we talk about pure cloud intelligence, we think about training and inference on the cloud. Data is collected by edge devices, is sent to the cloud, and inference is performed on the cloud or data is archived for later training. All on device, we means that data doesn't leave the device, never. This means that both training and inference are performed on the device. In the middle, we have a lot of fuzzy levels going from cloud edge co-inference, in-edge co-inference, on-device inference, where training happens on the cloud, and cloud edge co-training, where training is shared between the cloud and the device. The more you go toward the higher level where we have everything on the device, we reduce the amount of data that is exchanged, and because of this, we also increase the privacy. If we think about pure model inference, we have different possible architectural scenario where we have all the inference based on the edge device. The inference is based between part of the device and an edge server. The inference is divided by the edge device and the edge server, and for instance we have inference between edge server and a cloud data center. As you see, data move outside the device in the edge-based computation and the edge cloud computation, while in the device-based and edge device computation, data doesn't leave the device except for some pre-processed case where we have edge device computation. There are a lot of technologies to allow for this inference on the edge, such as model compression, model partition, model early exit, edge caching, and some others. Within the AI-SPRINT project, we have experienced model partitioning and model early exit technologies for on the edge inference. But today I will talk about training on the edge. Why do we want training on the edge? Well, also for training, not having the data leaving the device will increase privacy and information security, will reduce time and latency, will increase scalability because we have a lot of edge devices, and at the end of the day will reduce costs. When we talk about training on the edge, we can have different approaches as well. A centralized approach, a distributed approach, and a sort of hybrid approach where you have different layers in the middle. When it comes to techniques for training on the edge, we have federated learning, aggregation frequency control, gradient compression, DNA splitting, knowledge transfer, and gossip training. Today, we will focus on federated learning. What does it mean, federated learning? Well, in federated learning, we leave the data on the end devices. So we don't move the data, nor for inference, nor for training, to the cloud. The model is trained on the server, but in a way that preserves privacy. Why do we care about privacy? Well, these days we are observing that data privacy is becoming really a big hot topic. In particular, some companies, they hold enormous data and they use this enormous data to train algorithms. These algorithms, they are susceptible to data breaches as well. Other applications like data, like AI generative models might also in a way impact privacy and might leverage on data which are not privacy preserving. Finally, the same models when deployed can be attacked to be de-anonymized. So it has been proved that it's possible to detect whether some particular item was used for training a model, even if just the model is released. So the point of whether you are entitled to use the data, especially in the medical and health scenario, becomes of utmost importance. Federated learning was invented for this. Federated learning is a machine learning setting where multiple entities that we call clients collaborate in solving a machine learning problem, which means in training a model, under the coordination of a central server. The data of each client does not leave the client, it's stored in the client. So we don't have the data leaving the edge devices. And the goal of the centralized server is just to aggregate information used for training. So federated learning is fundamentally different from classical distributed machine learning. If you think about distributed machine learning, data stored in a network of powerful cloud machines, it can be shuffled, it can be balanced, it can be exchanged between the client, and in a sense, any client has access to any part of the dataset. Here, the computation is the bottleneck, and typically you cannot scale above hundreds or thousands clients. With federated learning, the picture is rather different. You have a server which holds a model, initialize and define this model, and then it sends the model to the client. Each client independently performs some training of this model with its own private data, which is held private. Then it sends back to the server what is needed to improve the global server, and the server has to aggregate this information to improve the global model. Let me make an example taking the most known algorithm for federated learning, which goes under the name of federated averaging. So the centralized server selects a random set of k clients. It sends the model to the client. In this case, usually what the server sends are the weights that characterize the model. Each client, using its own data, perform one iteration of a training algorithm. If we think about an artificial neural network, we can have one or few iterations of stochastic gradient descent locally, and then what it does, it sends its own copy of the model parameters to the server. By doing this, each of the k client keeps the data locally, trains its own local model, and then sends this local model to the centralized server to perform aggregation. Aggregation that is performed on the centralized server by averaging, this is what gives the name of federated averaging, the contribution of each client to improve the model. And this repeats again iteratively by improving at each step the global model for all the clients. If it does not converge, we repeat until it converges. This algorithm was proposed originally in 2019 by Google for its keyboard. Each client, what was doing was computing a step of stochastic gradient descent locally on the messaging data collected from the users. The server was collecting just the gradients, that is the updates of the weights from several clients, and it was merging, aggregating this contribution into a global model. Global model which was delivered back to the user keyboards on the next round. By doing this, it was possible to improve a text prediction model without having a single sentence to leave the end user devices. This closes the first introduction to federated learning for privacy-preserving machine learning. In the next, we will see a few more details on federated learning algorithms.